Hello everyone, welcome back, and today we'll be talking about buoyancy. It's a really interesting concept in physics. It's the reason why boats float. It governs all of our lives at this point, so let's get right into it. Some important things to know before we start this is the concept of density, something we brought up way back in the first experiment. Density is represented by rho, and it's just the mass of an object divided by its volume. So it gives us two properties of an object all in one package, so it's pretty useful there. A second one is the volume of a cylinder. For those of you that may have forgotten, we represent the volume of a cylinder by pi r squared, where this is the area of the base of the cylinder times its height. So that's another important concept that's going to come up. And finally, one that you may not have heard of, called Archimedes' principle. Now, Archimedes' principle is what it helps explain the governing of buoyancy. So Archimedes' principle, there's a pretty interesting story behind it. This old Greek man named Archimedes was sitting in his bathtub with spheres of different metals and just playing around with them, and suddenly the idea of buoyancy came to him. He understood how it worked, and he ended up screaming throughout the streets naked, saying Eureka. And it's a pretty famous story. You've probably heard of Eureka. That's where it comes from. So what is buoyancy all about exactly? Well, it talks about the concept of being submerged in fluids. So what Archimedes' principle tells us is that if an object is in a fluid like water, or in fact air also, but for the purposes of this experiment we'll be dealing with water. If an object is placed in water, then some amount of water is displaced because of this object. For example, let's say I have some ball with a mass m and a volume v, so this is the volume, and I place it into a water container, so this is just plain water. When I place the object in, you can clearly tell that it's occupying some space by its volume, where water used to be. So now the water is actually going to get displaced. It's going to be moved away from where it was in this volume earlier, right? And so what Archimedes' principle tells us is that if the weight of the water of this volume is more than the weight of the object itself, the object will float. Alright? So that may be a complicated thing to come across the first time, but let's think of it this way. So I have a volume of water, again, just plain water. There's nothing in there. And then I take a volume that's of this size, so let me just draw that around here. This is our volume that's going to be displaced by an object. So when I place something in the water, it's going to move away from there by this volume. And we can find out what the weight of that volume is by using the concept of density. So what is the mass of the water in this? The weight of the water is going to be m of the water times g, right? That's just a normal concept. Now, where it gets interesting is this m. So we can represent m through the density equation. So it's density times the volume of water, density of water times volume times g. And the weight of the object is just the mass of the object times gravity, which again we can represent through density, the density of the object, the volume of the object times g. Alright? So this is what the weight of the water is and what the weight of the object is. Now we can go ahead and compare these two. We know that the volumes are the same because the volume of the object is displacing an equal volume of water. So what we're saying is that if rho w vg is greater than rho object vg, the object will float. So we can go ahead and cancel out the equal terms, and now we really see that it's all about the density. So if the density of the water is greater than the density of the object will float. This is why wood floats, because wood has a lower density than water itself. So if I replace row object with row of wood, we would get a density that's lower than water. Now the crazy thing is, this happens all the time. In fact, all of us standing right here are facing a buoyant upward force because of the atmosphere around us. Granted, it's very, very small, but buoyancy has an effect on us as well. Which is why when you place something in a fluid, there's an upward force acting on it from all around, right? So this is the main concept of Archimedes' principle. And so as we start to submerge an object in water slowly, the volume of water being displaced increases. And that's what the experiment today is all about. We are going to slowly lower an object into water and see how the buoyant force increases as more volume gets displaced. Is that right? So I'm going to go through 3 examples. One that's just very basic to help solidify the understanding of buoyancy, one that's more practical and leads to everyday life, and one that might help solve an old mystery. So let's discuss the first one. Let's say I have a very large sphere of volume, let's say 10 meters cubed, that's our volume, and let's say that the mass is only 10 grams. So I'm talking about something like styrofoam here. It's very large but very light and mostly filled with air. So its density is really, really small. And if I submerge it in water, now I place my styrofoam ball, so let's call it styrofoam ball in water, it's going to displace 10 meters cubed of water, right? So 10 meters cubed of water times the density of water, which we call 1,000 kilograms per meter cubed, and compare that to 10 meters cubed divided by only 10 grams, which is 0.01 kilograms over our volume, you can see that the weight of the water is much, much greater than the styrofoam ball, which is why styrofoam will float, because it's less dense than water. Now let's focus on a more realistic example. So let's talk about ships. Ships weigh hundreds of thousands of tons. So imagine a really large tanker that's in water and it weighs 45,000 tons. So how does something this massive float on water? Well, that's the amazing engineering trick that designers use when creating objects this large to float. The region of the ship that is submerged has a very, very large volume. So there's a certain part of the ship that's under the water, and then if you look at it from the side, you can imagine this is what it looks like. So this is the giant amount of volume that's submerged in the water, and if you replace all of that volume with water, you get something that weighs much more than 45,000 tons. And also considering that a ship taken as a whole has a lot of empty spaces, it's not a complete solid object, so the density overall of a ship is much less than the density of water in the same volume, which is why ships can float, because they're displacing more water than 45,000 tons. Speaking of ships, let's discuss how the Titanic sank. So the Titanic hit an iceberg and there was a rupture in the hull. Why did it sink? If ships this big can float, what gives? Well, what happened to the Titanic is when there was a rupture in the hull, water filled into the area, and so the volume of just ship there was now filled with water, increasing the weight. So now the water has to support the ship and its own weight, filling the same volume. So then at that point, when enough water fills up, it's occupying the same volume, and so it gets much heavier, and the water around it can't support the weight of the ship anymore, which is why the Titanic ended up sinking. Yep. Alright, so now we're going to do a problem that could very well save your life. So let's discuss this. Imagine being stranded on a desert island and all you have are logs, and there are 4 of you, and you need to find out how many logs you can use to float all of you safely back to mainland. So let's talk about the logs at first. We have a density for wood, which is 725 kilograms per meter cubed. Remember, this is less than water. Water is 1,000. And so let me specify that as well. It's 1,000 kilograms per meter cube. And we have a radius of the log, which is 0.08 meters, and a length of the logs, which is 3 meters. So we're assuming that the logs are cylindrical perfectly, and so this will help in finding out what the volume is. And the question also tells us that there are 4 people who weigh 80 kilograms each. So just simply multiplying gives us 320 kilograms of additional weight that needs to be supported by these logs. So let's go ahead and talk about Archimedes' principle once again. So Archimedes' principle tells us that the weight of the water should be greater, the weight of the water displaced should be greater than the weight of the object. So we know what the weight of the object is. The weight of the object is mass of the logs times n, where n is the number of logs we need, and we don't know what it is right now. So we're going to leave it as n times g plus, remember, this object also contains 4 extra people. So there's the weight, the mass of the people as well. And the weight of the water should be greater than this. So let's go ahead and cancel out all the gravity, acceleration due to gravity, because it's the same. And let's go ahead and start to figure what this is out. Just for simplicity, we're going to say it's equal. So you're just about floating, you're not sinking, you're not rising up, you're just staying at level. So we're going to say it's equal. On this side, we have n logs times the density of a log times the volume of the log. Right? So this is the same thing as n, no difference, plus 320 kilograms of people. And on this side, what do we write for the mass of the water? Remember, mass of water is water displaced. And the water is displaced by the logs. We're going to assume no people are floating in the water because that's what the raft is for. So the volume, so we're going to have rho of water times the volume displaced is going to be the same as the volume of the logs. So remember to put the n, because there are n logs, by r squared L. So that's what we end up getting, okay? We can go ahead and bring this over here. So what we really get is n by r squared L times the difference of the density of water and the density of the logs equals 320. So this is the additional weight that the water has to support. So you can go ahead and divide all of these things to find out what n is. So we get n equals 320 divided by pi. And I'm going to go ahead and put in the values now. R is 0.08. Yep, 0.08 squared. 3, and the difference between both of these, 1,000 minus 725 gives us 225. Oh, 275. Alright, so this is what you would get for how many logs. Let's go ahead and calculate it. And doing our magic calculation here, what we end up getting is the number of logs is around 19. So you need 19 logs to support 4 people that weigh 80 kilograms each that are of this volume, 0.08 radius and 3 meters. So that's how buoyancy and Archimedes' principle can help save lives as well.
Okay, so now we're at the lab setup. What we are trying to do is measure the buoyant force on this cylinder as we submerge it. So we're going to take small samples. We're going to measure the buoyant force when we submerge it just 5 millimeters, and then we're going to keep lowering it each time 5 millimeters until we get up to around the top. So we're going to see how the force changes over the depth once we change how far it goes down, right? Okay, so starting here we need to measure the diameter of the cylinder. So I'm going to take this vernier caliper. We've done this before in measurements lab. I'm going to measure the diameter this way. Okay, and then I get a value of 7.618. And then we need to calculate the area, right? So, luckily, I've already done this. I've taken the diameter, 7.618, plugged it into my area formula, where we have pi r squared, and r is just the diameter by half. That gives us a total area of 45.57 centimeters squared. Okay? So we're going to need that for our calculations later. Alright, next, first step, we zero this sensor out. We've already done this, so I don't want to do it again. We're just going to measure the buoyant force on the cylinder now. As you can see, it's not submerged yet. Okay? There's no contact between the cylinder and the water. So we take a sample, and we should have something close to 0 newtons on the cylinder. Okay? So we've done that. We have that value. 0.05 is close for our purposes. Okay? And then I'm going to now lower the cylinder into the water, 5 millimeters. Just like that. And now I'm going to measure the buoyant force. Okay? I'm going to do it again. So now we're down to about 10 millimeters. All right? And it looks like we're around double the value for our buoyant force. So we'll keep that sample. And so we're going to do this about 12 times, depending on how much water is displaced. We may not be able to go that far, but we're going to do that for about 12 times, get 12 values for buoyant force measurements, and then see what we get. Okay, so we've gone through and we've measured it at least 12 times. We have a buoyant force for every depth, and it does increase, as you can see, consistently. And so you can see here are our depths in millimeters. And so when we go over to make our graph, it's a nice linear slope. And so I select all of these data points, and I want to know what is the slope. Because in our lab, it asks us, let me see, somewhere in here. In our lab, it asks us to find the slope, force over depth. Okay? And here we've selected these, and I'm going to now find the slope, 0.0456. Okay? And so now we can use this to actually calculate the density of the liquid. In our case, it's water, right? And so if we take force over depth, which is our slope, 0.045, is equal to density times area times gravity. We solve for density. You should be able to find a nice value for water that's around 1,000, but you need to actually show that. Okay? One thing worth noting is that if we were to try this experiment in a much denser liquid, such as syrup, our buoyant force would be much greater because the density is greater. And according to our formula, that should be the case.